So in this video we're going to look at the conservation of momentum and how it can be used to explain the propulsion of spacecraft, ion thrusters and solar sails. So you need to be able to use conservation of momentum to describe and explain the change in momentum and the acceleration of a spacecraft due to the emission of gas particles or ionized particles. You also need to be able to use the conservation of momentum to describe and explain how the reflection of particles of light, which are actually photons, which we'll go into more detail later in the year, how they can be used to accelerate a solar sail out in space. And then you need to use vector diagrams to compare the acceleration of a spacecraft using a solar sail where these photons, so where light is reflected, with the acceleration of spacecraft using a solar sail whereby the photons are instead absorbed by the solar sail. So, firstly, imagine this spacecraft and the fuel inside the rocket or the spacecraft. They're in isolated systems. They're one joined system. So we're just going to pretend that initially the spacecraft is not moving. So initially there's zero. The momentum of this system is zero. So as we know with the law of conservation of momentum, the total momentum of the system. So if it was zero to begin with, then the total momentum of the system afterwards must remain at zero. Now, what actually happens is when fuel is propelled from a spacecraft, the rocket or the spacecraft gains momentum. The reason this happens is because the spacecraft's momentum, so we're going to let the spacecraft's momentum be PS for the momentum of the spacecraft, and the fuel's momentum be PF. So initially the momentum of the spacecraft and the fuel is zero. So therefore we can take PF from both sides. So the momentum of the spacecraft is going to be equal to the negative of the momentum of the fuel. So basically what we're saying is that the spacecraft's momentum must be equal and opposite to the fuel's. So the spacecraft is going to be propelled in the opposite direction, which is going to cause the spacecraft to accelerate. Basically what you need to be able to say is that basically we can explain the propulsion of a spacecraft. So in order for momentum to be conserved, as the fuel is ejected, the momentum before and after this, the ejection of the fuel, the momentum needs to be conserved. So as the fuel is ejected, that change in momentum, the change in momentum of the spacecraft is equal and opposite to the change in momentum of the fuel, causing the spacecraft to accelerate forwards. Now, ion thrusters are just a special kind of spacecraft propulsion system that uses electrical energy to accelerate ions to the rear of a spacecraft. It's just another fuel system for spacecrafts. And again, it just causes the spacecraft to gain an equal and opposite magnitude of momentum as these ions are ejected. Now, the benefit of this is that these are able to produce a small force on the rocket over a longer period of time, and this allows rockets to accelerate to very high speeds. This isn't so important to remember. Now, solar sails. So spacecraft are equipped with solar sails, okay? And a solar sail is purely just a reflective metal sail attached to a spacecraft, and what it allows the spacecraft to do is it uses the momentum in a photon. Now, later on we'll talk about light. Light can be thought of as both a wave and as a particle. And basically we can use these photons from the sun, these light particles, to help propel a spacecraft when it's out in space to conserve fuel. We can use the sun's energy in the form of photons to propel the spacecraft. So we're just going to pretend that the photon's initial momentum is P0, and when the solar sail reflects the photon, its momentum becomes minus P0, so its final momentum is minus P0. So we know that the change in momentum is the final momentum take the initial momentum, and our final momentum is actually negative P0 take our initial momentum of this photon, so it's minus P0 take minus P0. So the total momentum of the photon is minus 2 p naught. And as the sail and the photon make up a system when they're interacting, the change in momentum of the solar sail, momentum must be conserved as they interact. So if the change in momentum of the photon is minus 2 p naught, so to the left, then the change in momentum of the solar sail must be plus 2 p naught. So by having these solar sails, which are attached to spacecraft, reflect the photon, the change in momentum on the spacecraft is going to be plus 2 lots of the momentum of the photon. And you need to be able to draw a vector diagram. So excuse my drawing. So minus p naught. So initially, if we wanted to do a diagram of the change in momentum, first, it's hard to draw. Let me try again with the pen. So this is the initial momentum of the photon. This is the final momentum, because it's just negative p naught. So if we want the change in momentum, then it's going to be, the change in momentum is going to be the final momentum, which is minus p naught, and then it's going to be take the initial momentum. And if this is the initial momentum, then this is the minus the initial momentum. So the change in momentum is actually going to be minus 2 lots of p naught. Now, you need to be able to compare. So the learning intention was to compare the acceleration of the spacecraft using a solar sail where photons are reflected, which is what we just looked at, with a solar sail where photons are absorbed. So in this one, we're going to pretend that the photon is absorbed by the solar sail. So again, if this solar sail absorbs the particle, the photon, its final momentum is going to be 0. So the change in momentum of this photon is just going to be its final momentum, which is 0, take the additional momentum. So the change in momentum of this photon is going to be minus p naught. And then as the photon and the sail interact, the change in momentum between them must be equal. So if the photon's change in momentum is minus p naught, then the sail is going to experience a change in momentum of plus p naught. And this is only half the change in momentum experienced by a reflective sail, which was on the previous slide. So as change in momentum is directly proportional to the force applied, which then we know that force is directly proportional to acceleration, so we can say that a reflective sail produces 2 times more the acceleration than an absorbing sail. And this is why when manufacturers are producing spacecraft, they make the reflective sails, the solar sails, reflective rather than absorbing. And you also need to be able to draw a vector diagram for this. So initially, this is the change in momentum. This is the initial momentum. And the final momentum is 0. And if we want the change in momentum, then it's simply going to be the final momentum, which is 0, take the initial momentum, which is just going to be minus p naught. So the change in momentum is just going to be, this is going to be the change in momentum, minus p naught. So I just want you to have a go at questions 25 and 26. Maybe you want to have a read of the textbook pages on the previous couple pages, just because they probably explain it in a bit more detail than I do. And have a go at the questions. See me if you have any issues. Thanks.